Okay, so questions. Do you guys have any questions as we're getting started? Just finishing up that unit on application. So that test was due yesterday. Remember, you can still do it. There's a 2% late penalty per day up to 1 week late. So if you haven't done it yet, you can still do it. But you'll want to get it in as soon as you can. Let's see, I'm trying to think if there's anything else. And then you should be starting material on integration techniques this week. It's always more useful if you've given some problems a try and done a little bit of work before we go over them in class so that you have good questions to ask. So what are your good questions that you have to ask today? Cassie? Questions? I'm just picking on you because your name is at the top of the list because they're in alphabetical order by however you guys are signed on here. So you win for having that C name. Curtis, you're next. Okay, thanks, Cassie. Gabe, questions? Caitlin?
Nope, not at the moment.
You're good? Merrick?
Yeah.
Curtis, unrelated. Okay, the YouTube playlist should get updated each class period because I post the recording from each class period. So that's when you'll see new stuff there. You can also use those links in that are in e-learning to content related that's not me recorded, but links to Patrick JMT's YouTube channel, and he's got recordings on pretty much every topic. So his are shorter because they're just directed at like 1 or 2 problems related to specific topics, and a good way to see examples completed pretty much on anything. And they're named by their topic, so you can figure out what they're about before going in and looking at them. So for example, if you needed an application on finding volumes using the shell method, you could look in there on the links that I have and find something on volumes using shell method, or whatever topic you wanted to look at. Yeah, they're really nice, Curtis, and part of the reason why I haven't done my own necessarily like that is that he did such a good job on them. I hate to go back and sort of recreate the wheel when I would do something very similar. And Rob, you good? Okay, thanks. All right, so we're just missing the errands, 2 errands today. Okay, so if you didn't take your test yet, make sure you do so. I would try to get it done today just so that you're more caught up than behind, and then you can get going on the new material. So next up for us is integration techniques, which means we're going to sort of turn the corner a little bit and change topics. We've been working on applications since the beginning of the semester. There might be a few applications woven in here from time to time, but most of our work in the next at least 4 or 5 sections is probably going to be related to just sort of crunching out integrals. So some students like this better, some students like this worse. It just kind of depends on your preference. The good news is you don't have to set up applications here. I guess the bad news is you have to really brush up on your integration skills. So we're going to be looking at a variety of integration techniques. That was weird. Okay, I'm not sure what happened there. It was almost like my computer disconnected, but I guess it didn't. So I think we're all good. And we're still recording. Okay, so do you guys want me to show you a little bit? I'm not going to do a ton because I really want you guys to try to get in the habit of coming with questions. I know this is kind of a bad spot because you just had a test due yesterday. So it's hard to get started on the new material when you were probably trying to make sure you got that done on time. So we'll take a...
Yeah, I don't have any questions. You can probably just get, I mean, if no one else has questions, you can probably just get started with the content.
Okay, so let's see. To do this a little bit differently today. Actually, I shared screen, but I do want to I think this will work. Oh, there it is. All right, I got it. Okay, so I just dropped a couple of documents in the chat. They are the same document. So either, if you can open either one, that's fine. You don't need to necessarily get to both of them. So one of them is a Word document. The second one is a PDF, just some practice problems. And I would do these in Notability, but things have been weird since the latest update of iOS in using that. So I'm just going to use the whiteboard within, located right within Zoom, so that we don't run into that trouble that we ran into last week. So you got those 2 documents, and I'm not sure if I can add those to the whiteboard or not. Maybe not. Okay, so go ahead and we'll get to those documents in a minute. So integration by parts is sort of a technique that's used when we have a product that has too many factors in an integral. So the sort of classic example of an integration by parts problem is related to the first one you see on one of those worksheets if you've opened it. And I am going to, oh shoot, I'm sharing over here. Let's see if I can do this. This is going to be really ugly for a minute because I'm just going to type this. I'm going to just write this on here. I got to find my pencil. So this is just me writing with my finger, and it's kind of a A little mess there, so we can get rid of that. Okay, so I just want you to take a look at that problem for a minute. I'll grab my pencil, which seems to have disappeared, and think about why that problem is a little bit tougher than something we've seen before. Found it sooner than I thought I would. So what seems to be problematic about this integral x e to the x?
Just multiplication.
Oh, Merrick, you had trouble seeing those in the chat last time too, didn't you? Okay, I will post them again in e-learning, and I'll shoot them off in email to you in just a second. Yeah, there's multiplication, but we've had problems with multiplication before. So what about this multiplication makes this a little bit more difficult than what we might have seen before?
But you're gonna get constants.
I'm sorry?
Never mind. Disregard what I said.
Disregard? You don't want to say?
Well, I mean, you could use U substitution to solve for this.
Okay, so what are you going to let u equal?
X.
Okay, that is, it's like I planted you in the audience, Gabe.
Right, but then you would get du would be equal to just 1, so like you wouldn't have that x there. So
Okay, so let's be careful here, okay? So you just said, I'm going to write it down.
You'd have to use like 2 substitutions, like
you said let u equal x.
I said u equal x, yeah.
In a basic substitution.
Yeah. But can't you do 2 substitutions?
Okay. Slow down.
Oh, sorry.
Okay. This is what you said to do. So, and you said du dx is 1.
Yeah.
That means du equals dx.
Yeah.
Okay, so here's what you did to your integral. We're going to put in all those substitutions. X becomes u. E to the x becomes e to the u. And dx becomes du. Tell me how that integral is easier, harder, or the same as the one we started with.
It's literally the same.
It is the same. All we have done is change the name of x to u, and we didn't get anywhere. We didn't make things worse, but we also didn't make things better. So we're just sort of stuck there. And the problematic thing, so in a substitution, if you let u equal x, you are not going to improve things ever, ever, ever. In a basic substitution. Okay? So in a basic substitution, this idea of letting u equal x is not going to be helpful. We're right back where we started. Essentially the same as before. Okay, so we're going to have to come up with a different kind of plan. And where we're going to get it is to notice that we do have a product. So we're going to think back. To our product rule for derivatives. So we're going to just kind of put a hold on this problem for a minute. And we're going to just think back product rule. And remember, our product rule is not for integrals, it's for derivatives. But we also know that integration is the opposite of, or the reverse process of derivatives. So maybe there'll be some help here. All right, so what did the product rule look like? It said the derivative of a product, and I'm going to write this as a product using letters u and v. So the derivative of u times v with respect to x, with our du dx notation. Who remembers the product rule? I think we've used it recently. What was it? It was the first function, which we called u, times the derivative of the second, dv dx, plus the second function v times du dx. And in order to sort of get where we want to be in terms of integration, we're going to switch this over to the differential notation. In other words, think about this as multiplying by dx. So we can say the differential of u times v is u times dv plus v times du. And so then we look at this and say, well, that's kind of a mess. I see a differential on one side. Remember, the differential of something is what you get when you differentiate it, times dx. On the right-hand side, we have these sort of mixed differentials. We have u times the differential of v plus v times the differential of u. And it turns out that that's actually going to be helpful. So when you have an equation, what is the thing that has to happen if you do something to one side of an equation? So let's say I multiply one side of an equation by 2. What else do I have to do? I'll give you a minute to think about that. If I multiply one side of an equation by 2, I should also do what to the other side of the equation? It's not a trick question. Wow, multiply it by 2. Thanks, guys. So whatever I do to one side of an equation, I have to do to the other side. Well, I'm not going to go multiply both sides of this equation by 2. I'm going to look for the opposite operation. So what's the opposite operation to differentiation? It's integration. So what we're going to do is we're going to integrate both sides of this equation. We're going to integrate every term. So on the left-hand side, the integral of the differential is the integral of u times dv plus the integral of v times du. Now, that left-hand side might look messy, but it's actually the nicest piece of this. If I find the differential of something and then I integrate, where should I end up? Differentiate, then integrate, I should end up right back where I started, up to a constant. That means the left-hand side is just u times v. And the right-hand side is these two mixed integrals added together. Now I'm going to take that last equation and I'm going to rearrange it into what we're going to call our integration by parts formula. And then we'll see how that works with that example we looked at the beginning. So we have u times v. Actually, didn't want to put that first. Do a quick little undo there. The integral of u times dv. So in other words, this one. I'm going to put that integral by itself is equal to uv minus integral v times du. And this formula is what we call the integration by parts formula. The parts are the parts of the original integral, the u and the dv. What we have to do in order to use this formula is to sort of identify what we want to call u in the integration by parts formula and what we want to call dv. And the plan is going to be, or sort of the goal, is that the new integral, the one on the right-hand side, I'll put a little underline here, this integral. The plan is going to be that that integral is hopefully a little bit simpler than the original integral. So notice that the original integral has a product, and what's problematic of that product is that that x is sort of an extra x hanging around that we'd like to get rid of. So we're going to try to get rid of it by using this integration by parts method. Now, how do you memorize a formula? You write it down every time you want to use it.
I got a question.
Shoot.
So why couldn't you just manipulate the inside of the equation and set and multiply by ln, and then?
Okay, number one, ln isn't a thing we can multiply by.
Oh, okay.
It doesn't mean anything unless we have ln of x, right?
So it has to be equal to something?
No, if we're going to multiply by a natural log, and I'm using your words because you said multiply, then we would multiply by the natural log of x. However, we cannot multiply an integral by a variable expression, or we're going to change that integral.
Okay.
Right? I mean, we can factor constants in and out of integrals, but we can't factor variable expressions in and out of integrals.
Okay, I was just wondering because you would be able to bring the x down and then be able to multiply.
Okay, so I think what you really wanted to say was that you wanted to take the natural log of that. But again, you're applying a function to what's inside the integral, and that's going to change things considerably. So as an example, take a look at the integral of x versus the integral of x squared. The answer to the integral of x squared is not the square of the integral of x. So you can't just apply a function inside an integral and then undo it and keep things the same. It's a little bit different than what we had as an ability with when we were dealing with limits. You could take the log of an expression and then find the limit and then exponentiate. We can't do that with derivatives, at least not completely. We definitely can't do that inside an integral, or we're changing that integral significantly. So a warning sign that I'm going to give you based on Gabe's question is if your question starts with "can't you just ... the answer is almost always no, you can't just. And there's probably a simple mathematical explanation behind it, or at least a moderate mathematical explanation behind it. But we can't simply throw in a natural log inside an integral because it might simplify things. Where did the negative sign come from? Aaron C., I subtracted integral v du from both sides. Notice that now one of those integrals is by itself on the left side. If I wrote one more step, I would have had integral u dv on the right-hand side. You're welcome. All right, so we've got this integration by parts formula. We're going to go to page 2. Actually, it looks like I was already on page 2. I'm not sure why. No, you know what? We're going to just do another one. All right, I think we'll be okay here. All right, so back to our original problem and our formula that we just came up with. So we had this one, that. We had integral of x e to the x dx. And we came up with this integration by parts formula. I'm going to call this IBP. Just to give myself a little bit more room here. It says if I have the integral of u times dv, that's going to be u times v minus the integral of v times du. So one thing to notice is that the left-hand side needs to match up exactly with whatever you are given. So in other words, we're going to sort of connect this integral with the left-hand side of our formula. And we have to use everything. In other words, something has to be called u, something has to be called u, and something has to be called dv. And when I assign those things, I have to use everything in my original integral. Every single thing. I don't get to leave anything out. Most of the time, you can kind of take a quick guess and sort of divvy things up, but do notice that your dv will always include your original dx. So we're not going to leave that out. Now, we want u to be something, hopefully, that gets a little bit simpler when we differentiate it. So, what are my choices for u? Well, I could use the x, or I could use the e to the x. Those are really my only two factors. All right, so which one of those do you want me to use for u? And remember, we're not doing a basic substitution here, so it is okay if you wanted to use x for u. Remember how that didn't work with the basic substitution? But it might work here, so let's see what happens. I'm going to let u equal x. dv is e to the x dx. Notice everything has been chosen. It's like choosing teams in your elementary school gym class. Everybody has to get picked eventually. I was always last or close to last because I was a wimp. So everybody gets picked. The x is in there, the e to the x is in there, the dx is in there. Everything is accounted for. Now, notice over in my, let's see, grab my little pointer. Notice in my integration by parts formula, there's the left-hand side. I've assigned u, I've assigned dv. This is equal to u times v. So I'm going to have to compute v minus integral v du. I'm going to have to compute du. So I'm going to do that here. And this is where your keeping track of whether you're differentiating or integrating skills are going to come in handy. If I have u, I'm going to differentiate to find du. All right, so if u is x, what does du equal? see. You guys are being quiet. Did anybody type it in the chat? If u equals x, then du equals dx? Didn't we just do that? We did that in the substitution problem. So we've got our du. Du is dx. We're taking the derivative. The derivative of x is 1. That means the differential du is the same as the differential dx. If we have dv, in order to get to v, we're going to integrate. And we're going to leave our constant of integration off until the end. So tell me about integral of e to the x dx. What do you get when you integrate e to the x?
Yeah.
I get e to the x. And again, this is the one place we get to leave off our constant until we get to the end. So we're going to leave that just like that. Okay, so we now know what u is. We know what du is. We know what dv was. We know what v is. So we've got all these little parts to our integration problem, hence the name integration by parts. Now I'm ready to go and plug everything into the formula. Integral of u dv is integral of u times v minus integral v du. And I'm just going to do some copying. Okay, so original problem was x e to the x dx. Oops, and apologies, that first one's not an integral. It's the whole point of making this easier. U times v, x e to the x. Integral of v times du. V is e to the x. Du is dx. So there's where we are right now. We used integration by parts. We now have a product that's not part of an integral, so that's nice. And then we have this new integral, integral of e to the x, which we actually just did. And integral of e to the x was e to the x. And now I'm done integrating, so I'll go ahead and put in my constant of integration. Integral of x e to the x dx is x e to the x minus e to the x plus c. Now, how do we check any integration problem? What'd you say, Gabe?
Derivative.
Derivative. All right, let's take the derivative of our answer and see what happens. We'll just go add another page. If I let y
Back for a quick second.
hang on one sec. I'm going to write this down and then I'll go back.
Okay.
There was my answer to that integral problem, right? All right, so let's, that one. There you go. There's the previous page.
I'll let you know when I'm done writing it. I only got a couple more.
Okay.
Thank you. I'm done.
You're welcome. All right, so let's go look at our check. which, oh, what happened to that other page? My y equals x e to the x minus e to the x plus c. So a quick check is to take the derivative of this, and we should get our original problem. And this requires the product rule. It's an equals, it's not showing up very well. First times the derivative of the second. Derivative of e to the x is e to the x. Plus the second times the derivative of the first. Derivative of x is 1. Minus the derivative of e to the x, also e to the x. Plus the derivative of a constant, but the derivative of the constant is 0. And notice that these two terms add up to 0. So y prime is x e to the x, just as we expected or wanted to have happen, because that was our original problem. Our original problem was integral x e to the x dx. And those guys match. So we know we're right. Integral x e to the x is indeed x e to the x minus e to the x plus our constant of integration. If we have a definite integral, we just go ahead and evaluate it like we did before. So if this integral were an integral from, say, 0 to 1, you do the same thing you would have done in the past. You plug in the upper limit, plug in the lower limit, and subtract and get your final result. Okay, so I think I'm going to try the next one, and I'm going to actually go back to, I don't know why I have, it says I have 5, but that one's, I don't know, not showing. We're going to go back to page 1 because it's empty. So let's try another integration by parts problem. This one's going to look maybe a little bit different, but try it anyway. And this is the second one on that handout, so you guys can see where I'm getting these from. This is integral of natural log x dx. So this one looks a little bit different in that I don't really see necessarily a product other than the ln x times dx. There isn't an extra factor hanging about here. But I still do have this problem that I don't have a formula for an integral of a natural log function. You might remember back to ln x having something to do with 1 over x, but that's not the integral, that's the derivative. So we're actually going to use that to our advantage. We need to pick a u, and we need to pick a dv. dv has to contain dx at the very bare minimum. For u, you want to pick something that gets simpler when you differentiate it, and something that's relatively easy to differentiate. For dv, we want to pick something that's relatively simple to integrate. In other words, I would say no harder than integration by substitution. If you have to use some fancy technique to get the integral that you need, then you made your dv too complicated. Integration by substitution is okay, but I wouldn't go beyond that. Since I don't have a formula for integrating a log function, I'm going to make that my u. I'm going to let u be ln x. Notice that I've used everything from my integral. I used my ln x here in u. I used my dx over here in dv. And now I'm going to figure out what all my parts are. This is the part where you want to make sure you don't make any errors. You're going to differentiate to find du, and you're going to integrate to find v. All right, so take a minute and do that. See if you can come up with a du, come up with a v, see what you get. And then we'll put all the parts together. Okay, so what'd you guys come up with? What's the derivative of ln x?
1 over x.
Yeah. Yep, so du is 1 over x dx. And the integral of, this might be helpful, you can think of this as 1 dx if you need to. The integral of dx is what has a derivative of 1?
X.
X. So that's kind of the way that rumbles together. All right, so now we're ready to go with this, and we're going to write down our integration by parts formula. U times v minus integral v du. U times v, so ln x times x, minus integral of v times du, x times 1 over x dx. And I'm just going to make that a little bit nicer looking with the x out in front, x ln x. And I'm going to multiply integral of 1 dx. Notice something that happened here, and it's not always exactly this, but it's often very similar. Notice that our new integral is an integral we already did. And this happens quite a lot. It might be off by, say, a constant or something, or maybe slightly off by a power if you start dealing with powers of x. But it's going to be a very similar integral to the one you just did. So x ln x minus x plus a constant. And I'll let you guys check that one. That's the integral of ln x. And now we have a formula for the integral of the natural log function. So figure out what the parts are, plug them into our formula, and then at least one more integral is left for you to do. So let's try another one. I'm going to have you guys try, oops, it's a little bit funky. Let's try integral, and I think this is on that sheet, of x sine x dx. So remember, your first job is going to be to figure out what your u and your dv are, and then calculate your du and your v by differentiating. I'm going to abbreviate that, and by integrating. Okay, so pick your u and dv, and then compute your du and your v and see what you come up with. So I'm going to have everybody try that one. Okay, you guys should be able to help me out now.
I got u equal to x and du equal to 1 dx.
Okay, remember you have to use, okay, du equal to 1 dx. Okay, sorry. I heard you wrong.
What do you think I said, dv?
Yes, I did. Okay, so, and that 1 is optional, right?
Yeah.
Okay, what do you have for dv?
1. Shoot, sorry, I muted myself. One for dv. 1.
Okay, so now I gotta, remember u and dv have to use everything. Nothing is allowed to get left out. So I used
Line of x.
only x for u, which by the way was a good choice. But that means dv has to be everything else. It has to be sine x dx. Yeah, thanks, Curtis. Do you see how that works, Gabe? I don't get to leave anything out.
Okay.
Everything has to be accounted for in that top line.
Could we have let u equal sine of x?
You could have, and I will show you what happens if you had done that.
Yeah, because that's what I started out doing.
Right. So here's the thing. If you let u equal sine x, then you get to differentiate it, which isn't that big of a deal, right? Derivative of sine x is cosine x. But then your dv is x, and your v is more complicated than before. You go up from an x to an x squared over 2. So generally, you want to try, if you can, to have u be something that gets simpler when you differentiate it, or at least doesn't get more complicated, which means
Okay.
things like polynomial functions, powers of x, are really nice choices for u. The same with a log function. Since we don't have a formula for integrating logs, logs are good choices for you because we can say, oh, well, when we differentiate them, at least the log is gone now. Choices for dv, oftentimes our trig functions are nice there, although they're not extremely harmful in choices for u. Just depends on what the other function is. And I'll give you a little way to remember sort of how you can maybe choose your u function wisely. Okay, so back to our dv equals sine x. What is the integral of sine x? Be careful.
Cosine. Cosine x, I mean?
Yes, it would be negative cosine. Thanks, Curtis. Negative cosine x. All right, so now let's write down our formula. Integral u dv equals uv minus integral v du. I'm going to hope to get this on one page. uv negative x cosine x. I'm going to put my negative sign out in front. Minus the integral of v times du, negative cosine x dx. And again, notice I don't need the 1 there. Nicely, those two minus signs are going to cancel each other out. That'll be a plus, plus. And I just finished this up by integrating cosine x. It's not the exact same integral as before we integrated sine x, but it's similar. And what is the integral of cosine x?
Sine x.
Sine x. So I end up with minus x cosine x plus sine x plus c, and that is my answer. And you can check, it's going to fit.
Do we have a test next week?
Do we have a test next week? You got the schedule too. Let's see. I have your next test due on 10/11.
All right, thank you.
So not this coming Sunday, but the next Sunday.
Okay.
Sunday is the 4th. So the next Sunday is the 11th.
Okay.
All right, so let's go try another one. This says I have five pages, but the 5th page, it just seems to not be showing up for whatever reason. So we'll just do that. All right, let's try another one. I'm going to try, see if you guys can get one started. Let's go integral Actually, I'm gonna go look in Word. So let's see, on that practice problems worksheet, we did number 1, number 2, we did number 4, actually. And let's see, we're gonna go jump up to number 5. So I'm just gonna change that X to an X squared. Integral of X squared sine X dx. So let's kind of walk through this one together. This is very similar to that last problem. And so we should be able to attack it in a similar way. And this isn't a trick or anything, we really can. And a similar way to attack this would be to let u equal what? Last time we let u equal x, so this time I'm going to let u equal x squared. And dv is going to be everything else, so sine x dx. And that means our first step, our v, is the same as it was before, minus cosine x. But our du is different. It's 2x dx. So here's my u, here's my dv. I used everything. And integral u dv is uv minus integral v du. All right, let's put all the pieces together. U times v, x squared times negative cosine x. Make sure I get my negative sign in there. Minus the integral of v negative cosine x times 2x dx. So we'll do a little bit of cleanup there. I've got 2 minus signs again, so that's a plus integral 2x cosine x dx. And my first term stays. Okay, so we did integration by parts one time. We got a product, negative x squared cosine x, plus another integral of a product, integral of 2x cosine x dx. How are we going to handle this integral, this new integral we came up with? Is that an integral we can do by a basic substitution? Or does it look an awful lot like the integral we just did in the previous problem, except we've switched a sine for a cosine? So notice that what happened is that we ended up with an integral where we need integration by parts again. And this can happen. If I had put in an x cubed on this problem, we would have ended up needing integration by parts yet a third time. And x to the fourth would mean integration by parts yet a fourth time, and so on. So we'll also look at what we can do for that. All right, you guys help me out. If we need integration by parts again, what should I let u equal? I'm actually going to leave this in blue. Remember, we want u to be something that gets simpler when we differentiate it. What's going to get simpler the 2x or the cosine x? Sines and cosines are about the same level of complexity. And notice that if we did put the 2x over here with dv and we integrate it, we'd be back to our x squared. We just have sort of a circular argument. So for you, we're going to stick with the same route, the 2x. Thanks, Curtis. And the dv will be our cosine x. du is 2 dx, and v is sine x. So all of those integration formulas that you had from last semester, if you don't have them memorized, you're going to get them memorized very quickly because you're going to need them so often in here. And you don't want to have to be dragging back out a book or a formula sheet every single time. The problems will flow much more nicely if you've got those basic formulas committed to memory. All right, let's write everything in. Minus x squared cosine x, just copying that. We're using integration by parts again, so u times v plus u times v, 2x sine x, minus integral of v du. V du, 2 sine x dx. And so finally, one last integration. Plus 2x sine x minus the integral of 2 sine x, which is plus 2 cosine x plus c. And that last line should be our answer. All right, so what I'm going to do, what have I got? 1, 2, 3, 6. Okay. Let's try another one. So we'll just add another page. And we're going to try another from that worksheet. We're going to try integral of x cubed e to the 2x dx. And I'm going to, how's that problem going? Can anyone tell me what they let u equal? What did you guys try? Okay, Curtis says u equals x cubed. That sounds good. And that means dv is everything else. E to the 2x dx. So if you hadn't gotten started, there you go. There's things to get started with. And I'm going to pause this again on the recording again so you don't have so much blank space to go through. Okay, so I showed you my first integration by parts step. Notice the v has a factor of 1/2 in it, because when you integrate e to the 2x, that 2, the differential of the power is 2, and that 1/2 power comes into play. when we integrate. So working backward. Remember, integration is the reverse of differentiation. So we're going to get that 1/2 factor when we integrate there. Also notice the factor of 3, and that ends up leading us to a factor of 3/2 in our new integral. So we're going to have to use integration by parts again, and this is sort of a standard little thing. We'll kind of bar that off. Next time around, we'll let u equal, I'm just going to stick with the 3/2 x squared. If you want to, it's okay to pull the factor 3/2 out of the integral. Just remember when you do that, you're going to get 3/2 times everything on the inside, and that includes the u, v, and the new integral. So be careful with that if you factor constants out. I find it almost better, unless they get too large, to just leave them in. Notice also with that u equal to 3/2 x squared, du is 3x dx, so du is kind of nice. And dv is the same as before, e to the 2x dx. So v is the same as before, e to the 2x times 1/2. You're going to work through integration by parts again, and then you're going to be careful with all your signs, and then you're going to have to work through integration by parts a 3rd time on this one. So keep working on it and see what you come up with. I'm going to pause us again. We'll go ahead and record again. Do you guys agree with me on what I have so far up there on the whiteboard? Merrick, Cassie, Caitlin, okay, at least 4 of you agree. That's pretty good. All right, I'm going to go ahead and distribute my minus signs before I finish this up. Minus 3/4 x squared e to the 2x minus minus, so plus integral of 3/2 x e to the 2x dx. So notice how those minus signs are getting built up so that we, and this problem is nice for this because there are no built-in minus signs in our integrals like there can be with sine and cosine. But notice how we're alternating signs now. So our first term is positive, our second term is negative, our third term is positive now again. And we're going to do essentially the same substitution as before. So one more time, and I'm going to even bar this off again so we can see where we have our next integration by parts step. And we're going to let u equal 3/2 x. And dv is the same as before, e to the 2x dx. du is 3/2 dx. And v is e to the 2x over 2. So let's see if we can get this on one page. X cubed e to the 2x over 2 minus 3/4 x squared e to the 2x plus u times v, so 3/4 again, e to the 2x minus integral of v du, which is 3/4 e to the 2x dx. Is that what you guys came up with? And then I think we're good. We have one more step, one more integration step. And so notice in that last step, the first 3 terms are going to stay the same. And then the last term is going to become a, see if I can sneak it in here, minus, I'm going to get another factor of 1/2. So 3/8. Oops, that's not showing up. We're going to have a little bit of cutoff here. So we'll see if I can. 3/8 minus 3/8 e to the 2x plus c. And I'm not going to rewrite the rest of it, but all of those other terms get repeated. Do you guys agree with me? So a couple things to notice. One thing to notice is that we ended up with this alternating sign pattern. The other thing to notice is that we got simpler and simpler expressions for u, and that's because our original u was a polynomial function. And finally, third thing to notice is that the integration was relatively simple. We were just integrating an e to a power, and we just had to make sure that we put that factor of 1/2 in every time. But it was kind of a repetitive thing over and over again. So we can actually sort of pull all this together with a little sort of trick to simplifying these multiple step problems, and it's called tabular integration. So I'm going to show you how that works. So I have two big things left to show you today, plus one more example. So the two, and I guess big things doesn't really necessarily mean huge. It's just that big as in important. Okay, so the first one is how you choose u. Choice of u. And you can actually kind of decide this based on the functions that you have. And I like to use the mnemonic I call it latte. So it's like a latte, but different. So if you use that mnemonic for choice of u and sort of choose left to right along sort of a stream of types of functions, then you're usually in good shape. So L stands for what kind of function do you think?
Linear?
Nope, more complicated than that. Although I get why you said linear, because we did have some linear functions in there, right? We had our plain old x. We're actually going to lump all of those in together. L stands for the one thing we didn't have a formula for integrating before today.
Log? Natural log?
Okay, so a natural log is a really good choice for you. It's usually your first choice for you. Our second choice starts with I, and I'm just going to put I and V. Inverse trig will be our second choice for I, for you. And we'll actually see that in here. If we have time, we'll integrate the inverse sine function. A stands for algebraic functions. Essentially, this would be any kind of powers of x. They might be whole number powers like polynomial functions, but they might also be radicals because those would be fractional powers. So square root of x would be an example of an algebraic function. Notice this is kind of in the middle in terms of choices of u. The reason for that is that these functions are also relatively easy to integrate. So sometimes they're good choices for dv as well. T stands for trig, and it's not necessarily because trig functions are difficult to differentiate, but they're also very easy to integrate in most cases. So trig functions fall a little bit further to the right, although we can choose them if we need to. And finally, at the very end, E stands for exponential. And again, we only choose those last for you because exponential functions are so easy to integrate. Since integral of e to the x is e to the x, it just gets shoved off at the end. Doesn't mean you can't ever choose it for you, but this is sort of a rule of thumb. choose log functions and inverse trig functions first, and then kind of work your way left to right. So it's just a little way to remember that. Now, the second big thing I want to show you is this little method, and I'm up to 8. I shouldn't run out, I don't think. We're going to go one more. This idea of tabular integration. And so this method works really nicely. It works and works well if u equals a polynomial function. So anything involving whole number powers of x, this works really nicely with. And in order to show you how it works, we're going to go back and I'm going to go look at that previous problem we did, the one that took so many steps, that one. Notice if we look at our final answer has an x cubed in it, which was our first u. And then the next term has an x squared in it, which actually was from a factor of 3x squared. So that was the derivative of x cubed. The next term has, oh, I didn't write my, I just noticed I have an error here. You guys didn't yell at me about this. This should have an x in it, shouldn't it? U times v, yes, it should have an x in it. So the derivative of 3x squared is 6x, and that factor is actually in there. And then finally, the derivative of that is a constant, and that constant factor shows up in the next term. So the way this tabular integration works is that if we keep differentiating u, we can figure out what all of the new u's are. And if we keep integrating dv, we can figure out what the new v's are. And we don't have to write this all out in this format because we know if that original u is a polynomial function, eventually we'll hit 0 for our derivative. So that's the key here. We have to start with a polynomial function, because if we do, we know we'll eventually hit 0 for its derivative. So let's go back here. So if u is a polynomial function, which it was for our problem, we're going to go put our example here, x cubed e to the 2x dx. It's called tabular integration because we're going to just set everything up in a table. So my first column is going to have my original u, and my second column is going to have my original dv pushing us off to a v. So u was x cubed. Now I'm going to fill in the left-hand column by differentiating until I hit 0. So I'm just going to start taking derivatives. 3x squared, 6x, 6, 0. You guys with me on that? So that's my left-hand column. My right-hand column is going to start with my original differential, e to the 2x. And you don't really have to put your dx in there. I usually put the first one in just to remind myself that I'm integrating, and then I skip them because the rest of them are my v's. So every time I integrated, remember I got that factor of 1/2. So my dv's are e to the 2x over 2, e to the 2x over 4, e to the 2x over 8, e to the 2x over 16. Now, if I number these guys, this was my first u, this was my second u, This was my third U. This was my fourth U. And my fifth U is 0, so I don't actually need it. This one was my original DV. So here's my first V, second V, third V, fourth V. Now I need to pair these up where they belong together. First U goes with first V, and so on. We need this blue. First U goes with first V, first U goes with first V, first U, or third U, fourth U. So those are the things that get multiplied together to form my U times V's. And once I have that, I'm all set except for one thing. And the one thing I'm missing is the signs, S-I-G-N-S, not S-I-N-E-S. S-I-G-N-S. Remember the alternating signs from our minus sign in our formula? That's going to come into play, and we're going to go positive, negative, positive, negative, and so on. Now be careful with those signs if you're working with, say, a sine and cosine function, because there could be some signs in the problem itself. In this problem, everything is positive, so that's kind of nice. But we should be able to get our result in here now by multiplying together our U's and V's. So U1 V1 is x cubed e to the 2x over 2 minus U2 V2 3x squared e to the 2x over 4 plus 6x e to the 2x over 8 minus 6e to the 2x over 16, and finally plus our constant of integration. And that was way simpler than working through the integration by parts. Although this is really integration by parts, it's just a way to keep track of all the U's and V's a little bit more efficiently. Does that make sense? Should we try another one? I'm going to have you guys try one with this tabular integration. We'll do one with a trig function. Let me see what I have on that worksheet. Oops. Let's try maybe one that's not as long. No, we'll do a different one. We're going to do one that wasn't on the sheet. Let's do integral of x cubed cosine 3x dx. So try this with tabular integration. Notice I have a nice polynomial expression here, my x cubed. So this should work. And again, I'm going to pause and let you guys work through it. So make sure you're careful with your signs and your constants as you're integrating that cosine 3x, and then you should be in pretty good shape. Give me another new yes, or maybe a yay. Why don't we put a yay, Y-A-Y in the chat when you think you have this one done, so I can distinguish this from the last one. Probably the biggest thing here is that worrying about the signs on the trig functions, the S-I-G-N-S signs. So Merrick, Aaron, Curtis, we're going to let Cassie and Caitlin work for a couple more minutes. And then we'll put this one together, and I think we'll call it good here. We could maybe do one more. But I think I'm going to leave one more for you to try on your own and see what happens with it. All right, good. We got everybody. So notice that every time we integrate, we're going to get a factor of 3 in the denominator. So that's going to be important. We're also going to flip from sines, cosines to sines and back and forth, and we're going to watch our signs, S-I-G-N-S. So let's see. Integral of cosine is sine. So sine 3x over 3 for our first u. Integral of sine is negative cosine. So negative cosine 3x over 9 for our next one. Integral of cosine is sine. So negative sine 3x over 27. Make sure you put factors of 3 in there. And then finally, integral of sine is negative sine. So cosine 3x over 81. And those are our V1, V2, V3, V4. And we should be able to multiply those together. Notice the little angles with our sign changes. So the first and third get pluses, second and fourth get minuses. And we'll put everything together. So x cubed sine 3x over 3 minus a minus, so plus 3x squared cosine 3x over 9 plus and a minus, so minus 6x sine 3x over 27, and then minus 6 cosine 3x over 81 plus c. Do we agree? And if you don't agree, check my signs because I could have made an error. I don't think I did, but I could have. And you might have simplified the fractions there, which we can certainly do, but this is fine as well. So notice we have a 3/9 that we could simplify to 1/3 and a 6/27 and a 6/81 that all simplify a little bit.
So no matter what we do, when we do integration by parts, will it always be alternating signs?
So the alternating signs come into play every time, but remember sometimes those alternating signs get canceled out because of the derivatives and integrals themselves. So when you're dealing with trig functions where you've got negatives in the derivatives and integrals, some of those can cancel. So notice how here the minus and minus gave us a plus. So that second sign ended up being a plus. And that third sign then went back to a minus. So there is that cancellation that can kind of throw that off sometimes, but the minus sign alternating is built in there because of the formula, because it's that first integral minus the next one. And then when you do integration by parts again, you're saying minus a bunch of stuff in parentheses, so you get a minus and then a minus.
Okay.
Yeah, so that alternating thing happens, but you're going to have to be careful with the signs. And also remember that this whole idea of tabular integration only works if your u will eventually have a derivative of 0, which means u has to be a polynomial function. It can't be anything else. And you also want your dv to be something pretty simple to integrate, right? You don't want to have to go off and do some other strange technique to figure out what your v is.
Okay, thank you.
Yeah. Okay, so I think I'm going to leave us there for today. I'm going to ask you to take a peek at one of those problems on the worksheet. We're not going to go through and do it. I'm going to tell you that it will require integration by parts 2 times. And you're going to have to decide what to let u equal to start. And then, of course, the second time as well. So the problem I want you to try is this one, integral of e to the x times cosine x dx. And then next time we'll look a little bit at evaluating these. We really did all the kinds of integrals for the most part. So we did some of the basic ones and some of the not so basic ones. But we'll do a couple more maybe not so basic problems next time. And then we'll also work on evaluating if you have any trouble with that part of it, but I don't think you will. It's just a matter of plugging in upper and lower limits as before. So do you guys have any questions for those of you who are left? All right, and Aaron C., I just saw you sent me an email, so I'll take a peek at that and get back to you.
Thank you.
You're welcome. Have a good day.
You too. Bye.